Hey everyone, we're back and we're doing section 1.2, which is all about sets. Okay, I'm gonna let you know something. Section 1.3, it's in your book. If you want to read it, you're more than welcome to read it. But I don't think it's worth doing a video on section 1.3 because if those things come up later in the course, we will introduce them later in the course. They're kind of niche things like Cartesian products and stuff like that. It's not really the direction I want to go anyway. So I'll define what a Cartesian product is in this section. And then the next section is all about, different kinds of sets and blah, 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 blah. And we're just not going to do it. So if you have questions on it, by all means, come talk to me. But I think we're gonna hold off on that section. So like I said, this is section 1.2, right? And it's all about sets and something called subsets. Okay. If you had linear algebra with me or someone else, right? Then we talked about vector spaces and subspaces, right? So what did that mean? It meant that like the subspace lived inside the vector space, right? And it's the same thing. These subsets are going to live inside these sets, okay? So first of all, we should talk about like what a set is. We know a lot of sets, believe it or not, right? The real numbers, the natural numbers, right? We learned all of those last time. And a set, in all honesty, it has a super like trivial definition. So a set, sorry, this is the definition. Okay. A set is a collection of objects. It doesn't matter what they are, right? It's just a collection of things, right? Like this right here. I have a thing of tacks right here, right? As you can see, my wall is white behind me because I moved into this apartment a couple days ago. So I haven't put up all the decorations, so I'm sure you'll see the wall evolve over the videos. But this little thing of tacks is just, it's a collection of tacks. So this is a set of tacks, right? We use set all the time, right? In our just normal everyday language. And it's really no different in mathematics, right? It's just a collection of things, okay? So we are gonna do some notation, okay? So let's talk about some notation here. I really do, and I truly believe this, the first part of the class is not mathematically challenging. It's very notationally challenging. Okay, so there's a lot of notation and keeping it straight, right? And like trying to remember like, oh, what is a universal statement, right? So there's lots of definitions. We're not going to be doing any proving or anything like that. The most proof heavy thing we're going to do, and I say proof very lightly, is like a truth table. Okay, at least for the first part of the class. And then we're going to jump into the fun stuff. Yeah. So like I said, try to keep the notation straight. If you're struggling with notation, come talk to me, right? And it really, 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 really is going to help you if you always try to use the proper notation, right? Because if I'm using one notation and you're using a different notation, that's not going to help us like sync, right? So try to use my notation. I'm using the notation in your book, right? So I'm not going to like, oh, this is like Nick's special notation. No, this is like universal notation that everyone uses. All right, that was a very big rant and I haven't written anything down yet. So let's talk about notation. So if S is a set, so we define sets with capital letters usually. right? So S is going to be our collection of things, right? This notation right here, right? We've already talked about this, means that X is an element of S, okay? So X is one of my objects that lives inside my set, okay? So there's another one, right? There's this right here, okay? So it's the element sign with the slash through it. It's kind of like the equal sign with the slash through it, right? And this means that X is not an element of S, okay? So that's what it means, right? There's two different types of notation. There is set roster notation, which is very useful for very tiny sets. And then there is set builder notation, which is, I would say, the more useful one, because most of the time our sets, we're not going to be able to write them down. We're just not, right? So, but let's talk about set roster notation, because sometimes, you know, it'll be helpful for us. So this is called set roster notation. Okay, and I think the best way is to do an example kinda, but a set roster notation is writing the elements between brackets. So I'm a very bad mathematician because I can't draw a bracket to save my life. I've gone to school for 7 years and still cannot draw a bracket. And I refuse to work on it because I'm lazy, I guess. So my brackets are terrible. If you can draw a great bracket, sweet. So let's do an example of this, right? So there's a bracket, okay? This set right here, this is the set, oh, let me say S. Sorry, let's redo this. Let's not smush it. So let's say S is equal to bracket 1, 2, 3. Okay, what is this? This is the set S containing the elements. Let's write it all out. Containing the elements 1, 2, and 3. Okay, so set S contains the elements, or it has elements. So let's say it has, set S has the elements 1, 2, and 3. Okay. So if we're describing a large set, right, it's okay to do something like this, right? So draw the line. 1, 2, 3. We can do ellipses. Okay, these are called ellipses. Okay. Oh, and I spelled that wrong. That's ellipses. Ellipses. Okay, that means it's 1, 2, 3, 4, 5, blah, 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 all the way to 100, right? So that's all integers, is what this says. All integers. 1 to 100. Okay. You know, these sets, they're finite, and I hate to break it to you, but a lot of sets aren't finite, they're infinite, right? Like the natural numbers, the real numbers, the integers, they're infinite. So you can also use ellipses to do this, to dot, dot, dot. And that is an infinite set. Okay, so this is this is natural numbers. Okay, that's what that set is. So S is the natural numbers. right? That just means it goes on forever. Okay. There's this like, there's this thing, set theory. So set theory is the oldest, one of the oldest, it's probably not the oldest, that's probably geometry, but it's one of the oldest types of mathematics. And if you were to ask someone who studies logic or set theory, they'd tell you absolutely not. If you were to ask someone who studies like analysis or algebra, which is probably not the algebra you're thinking of, but they would tell you that set theory is dead, which means that no one really studies it anymore, which is and isn't true. And that's not to say it's not interesting. That's to say that there's they found a lot about it, right? They found out a lot about it and no one studies it anymore because the stuff in it is like, the open problems are like really big problems. So there's a couple people who study it for sure. It's still very much out there, but it's very confusing and stuff like that. And I'll actually I'll post a video if one of you reminds me if I forget to talk about some set theory stuff. It's very cool and interesting. There's just a lot of it is known, is what I'll say. So anyway, set theory has all these weird axioms, right? If you took linear algebra, you know what an axiom is. An axiom is just like a rule, okay? They have one axiom called the axiom of extension. You do not need to know this name, but you do need to know what it does. So axiom of extension, what the axiom of extension says is it says that a set is determined by its elements, right? Not the order in which they're listed, or that some elements are listed more than once. So it says a set is determined, by its elements. Okay, not the order of the elements, or how many times an element is listed. Okay, so yeah, that's what the axiom of extension is. And what does that mean for us? That means if I have like some big set A, let's say it's 1, 2, 3, and I have some other set B, which is 1, 1, 3, 2, 1. Okay. Those are the same set because set B is just 1, 2, 3, right? But it's listed 1, 3 times and it has the order change. So order doesn't matter in sets. Neither does the amount of time that you list an element. So what this says is it says that set A is actually the same thing as set B. They're the same set. Okay, so that's what the axiom of extension gives us. Okay. Some pitfalls, because I enjoy doing pitfalls. Things you want to be aware of. This is not the same. They're not the same thing. Okay. What is this? That is the symbol or number 0. Okay. What is this? This is the set containing. Whoa, that's not containing. Containing 0. Okay. They're not the same. Okay. That's something to be aware of. Let's do another example. Okay, stop. Let's do an example here. Okay. How many elements are in this set right here. Okay, that's really what we want to do, right? So the answer, right, is the answer is 2. There are 2 elements. What are the elements? Well, we have 1 and the set whose element is 1. So the elements are 1 and the set whose element is 1. Okay, so that's another thing to be aware of. Okay, if we scroll back up here, just in your head, how many elements are in B? The set B. Think about it. Okay, the answer is 3. Because when we say elements, we really mean unique elements. Okay, because we can write the set B as the set of 1, 2, 3. Okay, so since we can write them the same way, then it only has 3 elements. Now, I know this is very confusing for those of you who code, because if you don't code, ignore what I'm about to say, because like in strings and stuff like that, like you can have things listed more than once and you say pick the 5th element and it doesn't pick the 5th most unique element, right? It just picks the 5th thing in the list, right? So it's different in that sense. Okay, so but if you don't code, ignore what I just said. Okay, that set roster notation, lucky for us, we already know what the real numbers and stuff like that are. Let's I just want to do a couple other things. So other symbols. Okay, so other symbols, this symbol right here, we know that's the integers, but if I add the plus sign, right, that is positive integers. Integers, right? I could do R plus, right? The R with the plus sign, and that's positive real numbers. If I do the minus, right, that's negative, right? So I wanted to kind of just throw that out there because it's gonna come up pretty soon here. There's also this one, so which we're never gonna use really. Oh, I don't know why I wrote my Z that way. It's you write Z and then non-neg, which means non-negative. So this is just the positive integers with 0, right? So this is non-negative, which just means it includes 0, non-negative integers, right? And you can include any of the subscripts, or sorry, the superscripts, which is like the little power thing, with any of the big sets we have. Okay. So let's talk about set builder notation. This is probably, this is what it all comes back to. Okay, it all comes back to set builder notation. This is what we're going to use in the class. This is how you're going to write proofs. This is it, right? So let's talk about it. So set builder notation. Okay. All right. So we're going to say let S be a set. And we're just going to say it's going to be very weird, but it's the definition. P of X be some property. Okay. Be some property that all the elements may or may not satisfy. Elements of S may or may not satisfy. Okay. So we're going to define this thing, and this is how we're going to write it. So we're going to write X in our set S with a bar, okay, P of X, okay. So this is set builder notation. I'll make the bar a little less exaggerated. This is what set builder notation is. And I'm going to write this, what this means in words, right? This means the set of all elements in S, this little bar here means such that, okay, such that those elements have the property P of X. Okay, that's what that means. Okay, so we're gonna, like, you can digest it, right? So you can hit pause, but we're gonna do examples. That's just what we're gonna do for the rest of the time. Okay, so I'm gonna, like, stop and I'm gonna say questions, and obviously you guys aren't here, so if you have questions, just email me. So here we go. Let's, like, write out what some of this means. So what does, we'll do two of them. So X in the real numbers, okay, such that -2 less than X less than 5. Okay. What does that mean? Okay. So what does this mean? Okay. So X is a real number. Okay. So, and we are somewhere between -2 and 5. That's what it means. It means I'm living in my real numbers, but I'm only between -2 and 5. So if I draw a number line and I have -2 and 5, I'm the open interval between both of them. Okay. That's what I mean. Okay. That's what that set builder notation means. Okay. Not to be confused. Let's do a different example. How about this one? Instead of X being in the real numbers, let's make X in the integers. Okay. Such that we're between -2 and 5. Okay. What if that's the case? Well, if that's the case, I can actually list these, and I'll list them, because I'm only the integers. So I can't draw the number line, right? Because then I would get things that weren't integers, right? I could get like -1.5. So this set is just -2, -1, 0, 1, 2, 3, 4, and 5. That's, sorry, and it's the open interval. So it's not -2 or 5. Right? So that's the difference between them. Okay. So you have to make, like, sure of what your set is. So if it's just the integers, you don't want any decimals, you don't want any fractions. If it's the real numbers, then you can have any number you want in between. Okay. Okay. So I think that's it. We could do, yeah, no, I think that's it for sets. We're going to define a subset real fast, and then we'll be done. Okay. So a subset, like I've said before, is just a little tiny set that lives within your big set, right? So subset. Okay. So let A and B be sets. So we're going to have two sets here, A and B, that we're working with. Okay, we say A is a subset of B. Okay, A is a subset of B, and we write it this way. A, so it looks like less than or equal to, but it's kind of like a C instead. Okay, so A is a subset of B if and only if every element of A is also an element of B. Okay. You could also use A is contained in B, right? That's also fine too. Okay. So here we go. Let's do an example and then we'll get to like the little niche thing here. So if A is the set 0 and 1, okay, and B is the set 0, 1, and 2, okay, that means that A is a subset of B, okay? Because look, every element in A is a subset of B. Okay, or every element in A is also an element of B. Okay, so let's take a breather here. If A was this though, 0 and 1, and B was 0, 1, and 2, right? A would not, which is how you write that, not be a subset of B. Why? Because A is the set 0 and the set containing 1. Or sorry, it's the set containing 0 and the set containing 1. Okay. B just has the elements 0, 1, and 2. Right? There's not this element right here, right? This isn't 1. That's the set containing 1. So it's not true. Okay. That's just something to be aware of. Okay. Okay. If you look at the above definition, technically, by the above definition, if A equals B, like if they're the same set, then A is a subset of B and B is a subset of A. Okay. So I'll say then and. Okay. That's by the above definition. Okay. That's what technically that means. Okay. So we have this thing called a proper subset. Okay. A proper subset. And all that is it says there must exist. I'll say if A is a subset of B, there must exist at least one element in B that is not an A. Okay, so that's kind of the whole caveat there, right? So for us, we're always going to be talking about proper subsets. Otherwise, we just say they're the same set. Okay. So that's really all I want to talk about. Okay, the Cartesian product is in here. You know what a Cartesian product is. It's the stuff on the XY plane. So like an ordered pair, that's just a Cartesian product. So you know, we'll talk about it later. It's just not useful for us right now, but it'll be useful for us later. Okay. So that's it. If you have any questions, let me know. If not, I will see y'all next week.